Okay, everyone, it's that time for another statics exam problem here. So this problem is this is actually one of my exam problems when I took statics. This is going to be, I believe it'd be fall 19 is what this exam is from. So you guys are keeping track at home. So fall 19, this is problem 4. Oh, fall 19 exam 2, problem 4. So this is something that I had in my exam 2. This is kind of a frame problem. So we'll go ahead and get through this. This is something you should see something similar to this on your coming exam. So the question reads, for the frame shown, the pulley has a radius of 1.5 feet. So we can just go ahead and maybe draw that little dimension in there. 1.5 feet, like that. So question A is determine the support reactions at A and E expressed as a magnitude and direction. And it says indicate direction by an arrow with appropriate angle. So that just means that instead of saying AY and AX, you're gonna find your AY and AX, but then you're gonna use the distance formula or Pythagorean theorem or whatever you want to call it, and then the inverse tangent to find what those are. So that's not too difficult. And then the next problem is suppose that the support reactions at A and B, does it say A and B? A and B right here, were rollers instead of pins. What term would describe the frame system if that were the case? Actually, my bad. I believe when I took this exam, they wrote in B, and they told us in the middle that it's supposed to be E. So A and E are rollers instead of pins, because they're both pins in this case. What term would describe it if that were the case? Well, we can go ahead and talk about that later. We'll go ahead and get started with problem A. I always like to start with a free body diagram. That should always be your first thing to do, your first thing to look at. And obviously it says no points will be given without proper FBDs. So free body diagrams might not necessarily get you points in themselves. A lot of times the grading sheets don't say, hey, 5 points for this free body diagram. But if you don't put it in, we just won't grade it, unfortunately. I think there might be some cases where we would, but in all reality, probably not. So this is about what we got here. I just drew it as a simple line here. If we take a look at this, we can go ahead and draw on our reaction forces. So you've got AY going up, AX going to the, I assume, right and up. These are just assumptions for now. And then EY going up, EY to the right, because these are both pins. The next thing you got, I'm just going to draw a circle here so we know this is a hinge, because that's a hinge there. And then, let's see here. We can go ahead and draw in our pulley. Draw that in. And then we'll just go ahead and put our dimensions in. We'll do that now. So we've got from here to here, 3 feet. All the way to the end here. We split that up. It's going to be a 9 feet and 9 feet. Alrighty, and then let's see what else we got here. On the left end here we can draw our dimensions. I'm going to draw a little dotted line so we see where this is headed. We've got 6 feet and 3 feet to where the top of this pulley is. And we'll need that because that's where this rope is going to be, this cable. And then ultimately at this pulley, we've got this going downward at 210 pounds. And that looks like it's the only applied force. So if we look at this, we got all our dimensions in, we got the shape in it, our reaction forces, which you've got 2 at A and 2 at E, and then our applied force, which if we look at this whole thing as a whole and not split it up, all we can see it as is a force going down. We don't draw a force here in this tension, or in this cable here, because this cable here goes along this way and down here. So if we were to draw the force in here, it wouldn't be correct, because that would be the internal force of this rope. Well, as far as we're going, we're not looking at the internal force of the rope, we're looking at it as it's going down this way. So if you want to think about it, this rope is the same thing as one of these members. When we draw this free body diagram, we don't draw the reactions at C right now. My bad. Hopefully you guys were able to see all that. But we don't draw all the reactions at C right now because we have kept C intact. We haven't split it off. We will eventually split it off, I believe, to find what A and E are. But for the time being, C itself just is a hinge and we can't see the forces. Same thing with this rope here. So, and that was one thing that I really struggled with here when I took this in my exam, is I drew the force coming off this rope sideways, and I got quite a few points taken off for that. So it's always important to kind of take a look at the thing as a big picture as a whole, and make sure you know exactly what's going on, where the forces are acting. So we want the support reactions at A and E. Well, right now, we can solve for AY and EY. We can do that taking the moment of one of these points about the whole system. So we're going to go ahead and do that. Some of the moments, let's say about A. So some of the moments about this point here. The first thing that we can include is EY. It'd be going up. So EY. And this is 9 plus 9 is 18. 21 feet. EY times 21. And then here, the only other force that'd be causing a moment, because EY is in line with A, is going to be this 210 pounds, and it's going to be going down, or clockwise. So minus 210. And then the distance here, I'm going to go ahead and draw more dotted lines so we can kind of visualize. And then we've got a 1.5 feet here. So from A, the distance to where this force is acting is going to be all the way to the center of this pulley and then out to the radius. So 3 plus 9 is going to be 12, plus 1.5 is going to give us 13.5 feet. And those should be the only two forces acting on this. Or, I'm sorry, not the only two forces causing a moment about A. We'll go ahead and multiply that out. I'll get my calculator out here. I do not have an answer key for this problem, so if I do it incorrect or anything, just let me know. Be prepared for that, but I think I kind of got a good grasp on how to do this, that I should be doing it correct for you guys. But if I do make a simple mistake somewhere, let me know. But anyway, EY, I'm going to go ahead and draw a little scribbly line under there so we don't forget about it. I'm not going to box it like I was because it's not our final answer. So we've got EY. We could go ahead and sum the forces in the Y with AY and EY and the 210 to find what AY is. I like to be a little more thorough and sum the forces about E, or some moments about E, just so in case we happen to mess up this calculation, this one should be correct. So some of the moments about E, we've got, we'll go ahead and start with the positive, 210. This is going to end up being, it's 9 feet to the center, and we'll take it back the radius. So 9 minus 1.5 should be 7.5. And then we'll take our AY, so minus AY, and that's again going to be the whole 21 feet. And those should be the only two forces causing a moment about EY, or about E. So we figure this out. There should be 75 if I do the math in my head correctly. But I don't trust myself sometimes, so I'm just going to calculate it out. And it is 75. Okay. So these are our Y direction forces. Now we need to solve for the X direction. But right now we don't really have a way to do that because we can't exactly take the moment about anything. If we took the moment about this point, we don't see the EY. At this point we don't see the A, or the, oh, my bad, I drew that incorrectly. This is EX. We can't take the moments about these points because in the X direction these are in the same line, so they don't cause a moment. And we can't take the moment about here because we'd have AX and EX both included in the equation. And we can't really take the moment about, or we can't take the sum of the forces in the X because AX and EX are both in that direction. So ultimately what we have to do is we have to split this up into two free body diagrams of the frames. Now taking a look at the free body diagrams here, Let me see what our internal forces are. Ultimately, what we can do is we can solve for one of these x forces, either ax or ex, and then solve for that, and then use that to solve for it in the entire free body diagram. So let's say, I think what we're going to do is we're going to take a look at this little section here from A, B, C. And we're going to solve for what ax is, and then using ax, we're going to plug it into our free body diagram for the whole thing, and then use that to solve for ex. Now you could do that either way. You're probably going to have to solve for, you could solve for these c forces, and then draw another free body diagram for CDE to solve for ex. But either way, they both rely on the calculations that you've already made. And so I tend to look at whatever is going to be simplest. So if you're in the middle of the exam, it would be simplest to just make one free body diagram here and then put it into the whole free body diagram. And that'll save you time and hopefully save you some energy and effort. It's kind of like the opposite of what I was saying here, where I did both of these moment forces. This is just to be sure of myself. But in a case like this, you can't really find one force without finding the other force anyway. So there's no point in making extra work for ourselves when it's not going to be any gain. If anything, it might be worse because it's more calculations for you to mess up. So I'll go ahead and draw a free body diagram of ABC. So at A, we've still got our AY, which we calculated as 75. So I'll just go ahead and draw that in as 75 now. And then AX, which we don't know what that is. I'm going to draw a little dot at B. And then here we have C from up here. And neither of these are two force members. This one, CDE, almost looks like one, except the pulley really throws that off. And ABC is not one either because you can have that force there. So neither of these are two force members, so we still have to solve for CY and CX, or at least take those into account. The next thing is this cable. We need to include this cable because now we've kind of chopped off this section here. Let's say we made a little cut right there. It would be going through C. A little cut through C. Well, that cut through C is also going to cut through this rope. So this rope is no longer its own member, it's exposed. It's almost like exposing internal forces. And so because of that, we're going to have to draw in whatever tension this force is to be acting on this cord. So the tension in this force from this pulley, the pulley only transfers the force. We can assume that it's a frictionless pulley right now because you guys haven't learned about that yet. So we can assume that if this is 210 pounds in tension going down, on the other side this is going to be 210 pounds in tension. So we can go ahead and draw in our free body diagram 210 pounds. And then we'll need our dimensions. So I'm going to draw them off to the left here. Our dimensions to the left from A to B, which we'll draw there, and C. From A to B, we are given as 6 feet. And then from B to C, or B to the top, we have 3 feet. And then I'll go ahead and draw dimensions in the bottom too. We've got 3 feet down there. Let's see here. So that's our full free body diagram for ABC. That should have everything that we need. Ultimately, we just need to solve for AX, looking at this here. Don't let this CY and CX confuse you right now, if you get in the middle of this. They're just there because they need to be there. I'm sorry, I'm kind of not phrasing this right. But essentially, don't look at this problem and say, oh shoot, now I have 3 unknowns. I got CY, CX, and AX. I've got all these things to solve for, and I don't have enough equations. Well, ultimately, you would have enough equations because we've got 3 unknowns, and you can do 3 equations with forces in the X, forces in the Y, and then sum of moments. But right now, we don't really need CY and CX. Like I was saying earlier, we could use them in this free body diagram to solve for EX, but for right now, we're just going to solve for AX, and then we can use AX later on in this free body diagram, which, if that's not making sense now, stick with me, and we'll get to that point. So ultimately, I don't care what CY and CX are. It's kind of confusing. We need to get rid of them or eliminate them to solve for AX. So we're going to go ahead and solve for the moments about C. So we take the moments about C. We're going to have a few forces causing moments. We'll go ahead from the top to the bottom. So first we've got the 210, and it's going to be positive because it's going counterclockwise. Hopefully you guys know that by now. If not, it's right-hand rule, counterclockwise up there. If you don't know that by now, please, please, please work through some problems and try to practice with the right-hand rule and just get good at that. Because that's something vital, not just for this class, but in the future going forward. And then the distance is going to be 3 feet, perpendicular distance, so 3 feet. Next, going down, we're going to have AX, again, positive. AX times, this time, 9 feet total. And then we're going to have 75, and it's to the left at this point, so it's going to be counterclockwise, or I'm sorry, clockwise, which means it's negative. So minus 75 times the distance is 3. We can set that all equal to 0. Now we're going to have to solve for AX using some algebra, which is not too bad. Sorry for the glare there for my lamp. We'll go ahead. We'll take 75 times 3 minus 210 times 3, and then divide that all by 9. Because we add this, subtract that, divide it by 9. We've got AX is negative 45 pounds. Or ultimately, AX equal to 45 pounds this way. Now, we're not reporting our answer in Cartesian format or whatever. We need to put them back into their magnitude. So these arrows aren't quite vital now. I'm just using it to help me visualize it. So if we go back to our EY and AY, we drew them as lines going positively up on the free body diagram. So just for reference, you can draw arrows going up. This one, we drew it going to the right, and we got a negative value, so it would therefore be going to the left. Now here's where you're at a crossroads of what you can do now. We've got AX. So we can either use AX to solve for CX, and then use that to solve for CY. But there's really not, and then we can use that and draw another free body diagram for CDE and solve for EX. Or we could just use the AX we have here and put it into this free body diagram and solve for EX that way. I think that's a lot simpler of a way to go. Try to reduce the number of calculations and not have to draw a whole other free body diagram that you don't necessarily need. So we're going to go ahead and revisit whole FBD. And doing that, we're going to go ahead and sum the forces in the x direction. And if we sum the forces in the x direction, I'm going to go ahead and write it all out. We're going to have AX. There's no other forces in the x direction but EX, and it's going to the right as well. So AX plus EX is equal to 0. Well, AX we got as 45 to the left, or negative 45, plus EX is equal to 0. Therefore, EX is equal to 45 pounds, and it's positive, so it's going to the right. We go ahead and scribble under that. Now this is where we get to the part where we need to find the magnitude. We're not done here. We've got everything that we needed to solve for, but now we just need to get it into terms that they want. So magnitude and direction, and then by an arrow with an appropriate angle. I'll show you at least what I think that means. I missed points on this too because I didn't put it in the right format. I put it in Cartesian, so I lost a lot of points on this problem when I took this test, when I took the class. So I'm trying to show you guys ways of not missing, on how to not miss the problem, or miss the points. So we'll go ahead and start with A. I'll draw a little thing there. So here at A, we've got, in vector format, it's going to be negative 45 and then 75. So ultimately what we want to do is we want to have 75, 45, and then what we're looking for is what this force would be. And this would just be the reaction at A, and it'd be an addition of these. Well, we're going to do Pythagorean theorem to find that. So A is going to be equal to, should be the square root of 45 squared plus 75 squared. This will give us what our magnitude is. Get the handy calculator out. That glare. Square root of 45 squared plus 75 squared. we're going to end up getting 87 point, I don't really know, sig figs. 3 or 4 sig figs is always a good thing. For final answer, don't round to the end, but for final answer, you can put it like 3 sig figs is probably good. 87.5 should be pounds. And now we want the angle. So ultimately, they told us to draw direction by an arrow with appropriate angle. Well, that essentially means that we can find any angle we want just as long as we draw it correctly. Well, I think the most logical angle to solve for is this angle here, and we can draw it as such. And so when we try to solve for this angle, we'll call it theta for now. Theta is going to be equal to the inverse tangent of, we got the opposite first, so it's going to be 75 over, and then down here, 45 is the adjacent. And again, if you don't know trigonometry rules like that, I would highly recommend going back and studying those and working through them, making sure you get examples of those to be good at it. Hopefully you're good at it by now. But we ultimately get 59.03 degrees. Just write it as 59.0 degrees. But we need to make sure that we draw it correctly. So off to the side, I'm going to go, again, write it correctly. A, we're going to have as 87.5 pounds. And then the angle, because we solved for this angle here, we're going to go ahead and draw a little picture here. This should show you what the angle is. A little depiction like that, 59.0 degrees. And that lets whoever you're reporting to, whether in this class the grader, or if you're in the real world, another engineer or whatever, that lets them know what angle we're expecting it to work at. So that should be enough for them to see exactly where it's going. E is going to be kind of similar. I'm going to rush through E because hopefully you've understood it from A. It's going to be kind of the same thing. E this time is going to be positive 45 and then 135 going up. So we've got 135, 45. This is going to be E going that way. So E is going to be equal to, and these are the magnitudes, so you can always just draw like that. If it helps you clarify, 45 squared plus 135 squared. Ultimately, this type of notation, though, it's important to know, but in the terms of an exam, sometimes it can be helpful for error carry forward and whatnot, but as long as you just kind of show that you know the magnitudes, how to solve for those, you should probably be fine. I don't think we're generally terribly picky on notation like that. And we get 142.3. 142.3 pounds. And then we're going to solve for theta. It's going to be the tangent inverse. This time we can solve for the theta to the horizontal. I think it's always kind of a good idea to solve for the theta to the horizontal. That kind of is how we're used to seeing angles anyway. So that's what would make the most sense. So we've got opposite, which is 135. Adjacent, which is 45. Solve for that. 135 divided by 45. We get 71.56. So 71.6 degrees. We can go ahead and write that in our final answer. E, we have 142.3 pounds. This time it's going to be this way. 71.6 degrees. We can go ahead, double underline or box or however you mark your final answer. Make sure you mark your final answer. It's a lot easier for us to see where you're finishing and starting and finishing. These should be your answers, or at least the answers that I got for this problem. So that's our part A. That's what they wanted for part A, was the reactions at A and E. Now for part B, they say suppose that the support reactions at A and E were rollers instead of pins. What term would describe the frame system if that were the case? This is one thing where we might have covered it once or twice in lecture. I probably haven't covered it because it's again on the more conceptual side. But ultimately, this is just a vocabulary word that you need to know. This on when I took this exam was like maybe 3 points or something like that, but still they might throw something in there. So if you want to study some terms, I might come up with another video or something to let you guys know some terms that you want to know. But ultimately, you'll want to know that if these are 2 pins, we need to look at that. We don't, or I'm sorry, not 2 pins. If these were 2 rollers, we need to see exactly what's happening in this. The term that we're looking for is unstable, essentially. If you go in your textbook, they'll kind of explain what unstable is, but essentially unstable is when you don't have enough forces acting on this beam to make it completely safe. Or maybe not safe is the correct term, but just to hold back every other force that's acting on it. Because if for whatever reason these were 2 rollers, if we had a force acting on them in any direction, trying to think about it. If we had a force acting on them in the x direction, this thing would move and it wouldn't be static. There wouldn't be any force to counteract that. Or if we were to try to apply a moment, it really wouldn't counteract that either. So you just need to know that it's unstable. There's some other terms that you'll want to learn, but ultimately for part B, the term is unstable. And for those of you who are in civil engineering, you'll get into more depth with unstable in structural analysis. That's kind of why I'm being a little touchy with it, because we go into some deeper definitions in that, and I can't quite remember exactly how they talked about it in this, but ultimately you just need to know, maybe review in the textbook or whatnot, that unstable is when you don't have enough reaction forces to take care of all the forces going on in the system. So anyway, that's it for this problem. Hopefully it made sense to you guys. It was really difficult for me at the time, so I can understand getting confused with it, but ultimately when you're taking it, just try to look at it from the outside. Try to look at the big picture first and find out exactly what's going on. Remember that if you look at the whole free body diagram, this cable here therefore wouldn't be drawn as a force. It just wouldn't really have an impact on this whole system. The only force or external force for the whole FBD would be this 210. And then from there you can kind of dissect it like we did here and look at that. But ultimately, this is a frame problem that you very well could see on your exam. And I hope this made sense to you guys. Anyway, take care. Good luck studying.